In today's lesson, we are interested in developing an integral to find the area that is squeezed between two curves. More specifically, this is an example of what we're trying to accomplish here. I want you to look at this example and notice that there are two curves there. There is a curve that is represented by the function g of x, which is this curve. And then there's another curve that's represented by a function f, which is that curve. And we're interested in finding the area between them, which is in this case is the gray shaded region that you see there. So from our past knowledge, especially in chapter 5, we develop a method to find the area under a curve. More specifically, let's say if I want to find the area underneath the function f. Here's the function f. If I want to find the area under the function f from a to b, that's the shaded region from a to b. This is the area under the function f from a to b. Then I can do that by setting up an integral from a to b of the function f with respect to the variable x. I can compute this using a calculator or doing it by hand, and that's how I find the area from a to b of the function f. Similarly, say if I want to find the area of under the function g. Here's my function g. And again, I want to find the area of function g below function g from a to b, which essentially I'm looking at the shaded area right here. Then I can do the same thing. I can set up an integral from a to b of the function g with respect to the variable x, and that gives me the area under the function g. Now, if I want to find the area that's squeezed between function f and function g, then what I have to do is I have to take the area that I found for the function f, subtract that to the area that's under the function g, then I get the area between the two curves. In order to do that, I can set up an integral that combines the two. So area squeezed between two curves can be found by taking the area of the top function, the area under the top function, which in my case, or in our case, is the function f. This is the top function. Okay. And then subtract that to the area of the bottom function, and then make sure you integrate that with respect to x. This is how we find the area that's squeezed between two curves, which makes sense because I'm taking the area under f minus the area under g, which gives me that blank space, which is over there, we consider that the area between two curves. One other thing I want you to understand is when we are finding the area between two curves, make sure that there is a top curve and there's a bottom curve. All right. I guess to be more specific, when we find the area squeezed between two curves, when we set up this integral, essentially what we're doing here is we are adding a bunch of lines. We're adding a bunch of strips of rectangles. Lines are really strips of rectangles, so we're adding a bunch of these. We're adding the strips of rectangle that connects from the top curve to the bottom curve. We're adding a bunch of those strips of rectangles, and that's how we find the area that's squeezed between two curves. Okay. When we compute areas, make sure you read the question carefully, and it's always nice to draw a diagram so you know what you're doing. Find the area bounded by the function x squared over 2 along the x-axis, and the x-axis along the interval 1/3. Start by sketching what this function is. Now, this function is a quadratic function that has been compressed. So I'm just going to perform a light sketch here. So x squared is a parabola, and it's been compressed, so it's going to look something like this. I'm looking for the area bounded by this function and the x-axis from 1 to 3. So maybe this is 1, 2, and 3. I'm looking for this area, guys. Okay. Clearly, it is bounded by the x-axis from 1 to 3, so I'm looking for the area under that curve. Well, this area is not squeezed between two functions, it's just under the function f. It can be found by setting up an integral from 1 to 3, of the function, which is 1/2 x squared, dx. Bring the 1/2 to the front because constant can be brought to the front, and then integrate this. The antiderivative of x squared is x to the 3rd over 3. We're going to evaluate that from 1 to 3. So so the antiderivative here is 1 over 6x to the 3rd. Multiply those together. When we take the antiderivative and evaluate it at 3, we get 1 over 6 times 27. When we take the antiderivative and evaluate it at 1, we get 1 over 6. Taking their difference, 27 over 6 minus 1 over 6 gives us 26 over 6, which reduces to 13 over 3, and that's the area under that curve. Essentially, we're adding up when we want to find the area. We're adding up just basically strips of rectangles. Okay, and if we add those, this symbol means add. If we add those an infinite amount of time, then it gives us the area.